Well, greetings from Ellensburg once again. I'm wearing the same clothes as the last video because I'm actually filming it on the same day. This is it. This is the last video. This is the last lecture. We're putting together all the pieces today. We're putting together all the pieces. Hopefully we got some answers. Hopefully this will leave you in a little bit of wonder about how cool and crazy the place where we live is, how cool and crazy our planet is, and maybe hopefully help you understand what it is about this that I just think is why I got my degree in geology and why I'll never stop loving it, because there's so much mystery, but you can put all the pieces together and see connections that I just think are so cool. There goes a loud car. Last time we talked about exotic terrains, and it was a big picture story. And we were putting together grandma's quilt and smashing it onto the one square of the quilt, one piece of the quilt at a time, onto the edge of North America. We built the Rocky Mountains. The story of the Rocky Mountains is of course more complicated than I just made it last time, but it's as much as we need to know. We know that from 90 to 30 million years the Rocky Mountains were building. And we know that this exotic terrain story has ever since North America started moving west, is the beginning of the exotic terrain story. But today it's the exotic terrains of Washington. We're going to focus right here at home. We're going to kind of build the state of Washington from scratch. We're going to return to the Olympic Peninsula to talk about some stuff that I intentionally left out. And then we're going to zoom back out and we're going to tell a regional story. All right. We ready? Let's go. The story starts 200 million years ago. What happens 200 million years ago? You should know. 200 million years ago, Pangea breaks up. Make a little timeline for you here. $200 million years ago, our most recent supercontinent starts to split. And what happens at that time? Snapshot. Where's our oceanfront property at that time? We're talking Washington. Our oceanfront property's in Spokane. If we're talking North America, got oceanfront property in Salt Lake City. And as soon as that breakup starts, as soon as the Atlantic Ocean begins to form, the plate boundary, the western plate boundary, also changes and becomes an active plate boundary. What are our two plates? Farallon, North American. Farallon subducts beneath North America. That was our conveyor belt. And out at sea, out in the ocean, the gigantic ocean that covers like 3/4 of the world or whatever, there's all these little blobs that didn't quite make it onto the supercontinent, maybe got torn off of the supercontinent. I was going to mention this in the last one, but I forgot to. How could we tear something off of a supercontinent? How could we get continental material? Remember, one of those things next to Mount Stewart, one of those accreted terrains was gneiss. It's a metamorphic rock. It's craton. How could we tear that off? Just a quick side note. Can you picture Baja California separated from mainland Mexico. Do you know what's separating it? It's the San Andreas Fault. Baja California is an exotic terrain that's currently being ripped off of its continent. Continental crust being ripped off of its continent by the San Andreas Fault. In 50 million years, Hollywood, San Francisco, all of that's going to be on top of an exotic terrain somewhere in the Pacific Ocean. That's how we make these things. All right, great. Come on, get back with it. You got one final lecture. Stay on topic. I might digress a few times here. Bear with me, please. So what begins when the Atlantic Ocean begins to form? The other thing that begins is subduction on the west coast of North America. So we're going to put that on here too. Subduction. Subduction begins. Cool. Where were our composite cone volcanoes at the time? They were east of Spokane, 100 miles east of Spokane. Composite cone volcanoes in Montana. Why? Because of the subduction of the Farallon Plate. And that was how far back from the coast you needed to get to pop up those composite cone volcanoes. So our conveyor belt starts up and starts bringing all of these bits and pieces to Washington, to the whole West Coast. But today's exotic terrain's in Washington, right? So we're going to focus on Washington. The picture you want in your yellow books, page 46. Really simple diagram. Almost scary how simple it is. Exotic terrains of Washington. So, the first thing that you might notice, over here, we're going to work our way east to west, coloring it in yellow right now. Craton. That's North America. That's continental North America 200 million years ago. The first thing we're going to add on is this little chunk of stuff called the Kootenay Arc, or the Kootenay Terrain. Did it in orange. Kootenay Terrain. Let's get a date for that. Kootenay Terrain. 175. 175 million years ago for our Kootenay Terrain. I'm going to pause right here because we can't get this twisted. I'm not telling you the rocks are 175 million years old. Most of the time when we're given dates, we're talking about the ages of rocks. But we're not talking about the ages of rocks here. The Kootenay Arc is much older. The Kootenay Terrain is much older than 175 million years. 175, that's our age of accretion. That is when the Kootenay Arc stuck itself onto the side of the craton in the same way that you might stick your gum underneath your desk because you're done with it. Please don't do that. Okay, 175, moving forward in time. Remember, we're talking accretion dates, not the age of the actual rocks, right? 150 million. We're getting younger. 150. We have the Okanagan Terrain. Okanagan Terrain. Make that green. $150. Okanagan sticks on. So 150 million years ago, if you want to go surfing, you're going to Omak or Tenasket. And hell, we don't know exactly what these things look like underneath our big cow pie of Columbia River basalts. Could be 150 million years ago. If you want to go surfing, you go to Mattawa. Because you'll notice we've got some dotted lines here. Dotted lines going down. What's this? Columbia River basalts here. All of this. But these things continue underneath. Our patchwork quilt continues underneath. There's material in the Okanagan terrain that's Precambrian in age. The material is much older. 150 is when it's stuck on. Our coast is moving west. And like I just said, northeastern Washington isn't the only place to find this stuff. It's just the only place to find it where it's exposed. Drill down a mile right here, you'll find this stuff too. All right. Now we got this big chunk. In blue. Called it the North Cascades terrain. That's a gross oversimplification of what it is. It is not a single terrain. In fact, from yesterday, Mount Stewart, 93 million years old, serpentinite, 150 million years old, biotite gneiss of Wenatchee, 100 million years old. Those are three different terrains that we are all lumping together as the North Cascades terrain. There's more than 3 dozen that we know of, plus who knows how many more underneath Columbia River basalts. North Cascades terrain, we're going to give you a range of dates for that. 150 to 80. $150 to 80 million years ago. 70 million years. We're chunking on little bits and pieces to the North Cascades terrain. Rocky Mountains are building, starting to build. The coast, 80 million years ago. The coast is at Seattle. You want to go surfing, you go to Seattle. Sometimes I call it the coast, but it's not the coast. Of course, the coast is out on the other side of the Olympic Peninsula. But 80 million years ago, that coast was at Seattle. 80 million years ago, the coast was the I-5 corridor. Everett, Bellingham, Tacoma, Olympia, Portland. You get the picture. I probably shouldn't go there, but I'm going to make it a little bit more of a hodgepodge. You remember Mount Stewart. We talked about Mount Stewart, this 93 million year old blob of granite. There's a story within the North Cascades terrain. There's a story within that called Baja, BC. Baja is in Baja, California. BC is in Vancouver, BC, 2,000 miles apart. And here's the story. Mount Stewart, the granite from Mount Stewart, formed in Mexico. And along with many other bits and pieces, many other exotic terrains, was transported northwards up the coast of North America until eventually it stuck on here in Washington State. So what? How's that even possible? I can tell you for sure that there's some very smart geologists who've been working on this for a very long time. I can tell you for sure that there's a tremendous amount of field evidence that supports this. I'll give you 2 examples right now. One is called paleomagnetism. I can't remember if we've talked about this or not. We've talked about magnetic reversals of the Earth's magnetic field. And we talked about how iron minerals, little bits of iron in igneous rocks, as the rock is cooling, those little bits of iron align themselves to the magnetic field. And paleomag geologists who study this stuff, that's their whole career, can pinpoint where on Earth a rock was when it formed based on the way that the iron minerals are aligned. And there's some fairly solid evidence that Mount Stewart granite, when it crystallized, when it cooled, was in Mexico. Okay, well that's weird. We're not going to go any deeper in that because that's not actually the story we're trying to tell here. But one more piece of evidence for you, one more solid piece of evidence for some of our accreted terrains coming from Mexico. Right up here, the map's so simple it's not even on it. But right up here, yeah, I got the San Juan Islands. San Juans. They're absolutely beautiful. Take a ferry boat up there, you drive around, you buy some ice cream that's too expensive, it's all touristy. It's a really cool place. A dinosaur bone was found in the San Juan Islands. Just one. Just a single dinosaur bone was found in sedimentary rock on the San Juan Islands. And that dinosaur bone matches a species, and that sedimentary rock matches a sedimentary rock unit that also contains that species of dinosaur that's still found today in Mexico. It's the only bone from that dinosaur, from that species of dinosaur that's ever been found. It's in fact the only dinosaur that's ever been found in Washington State. Trucked up here from Mexico. Anyways, we're getting behind. What do we have? 250 or 175. Got to stay up on my timeline for you. 175 million years ago, the Kootenai terrain. 150 million years ago, Okanagan terrain. 150 to 80 million years ago. I'm going to put it in quotes. North Cascades terrain. It's in quotes. Why? Because it's a big old fat lie, and it's way more complicated than that, but we're not getting into it. That's like 300 level geology course stuff. We're in Geology 101. North Cascades terrain. And then 50 million years ago. I hinted at this in our last lecture. Boy, that's sloppy. Silesia. 50 million years ago. And Silesia is the star of our story today. What do we know about Silesia? Silesia, actually, let's hold off for just a minute. Remember our Olympic Peninsula lecture the other day? And we talked, in that lecture, we talked about how the Olympic Peninsula, Mount Olympus specifically, is not a volcano. Has never been a volcano. Never will be a volcano. It's not going to erupt. It can't. doesn't have a magma supply. Kicking a dead horse here. Mount Olympus, not a volcano, right? What kind of rock did we say that was all built out of? Metamorphic and sedimentary, right? Right. Mudstones, shales, scraped up off the ocean floor. Yep. Here's the part that I intentionally left out. I'm going to go back to this one. Haven't cluttered this up too much yet. We're going to use red. That right there is lava rock. Say what now? You heard me? That right there is lava rock. It's a horseshoe shape. It is called the Crescent Formation. The Crescent Formation. The Crescent Formation is basalt lava rock. Man, we talk about basalt lava rock a lot in this class. It's because there's a lot of it around here. The Crescent Formation is made of basalt lava rock, but it did not come from Mount Olympus. It did not come from the Olympic Peninsula in any way, shape, or form. It was brought in. So I'm going to give you an age for the Crescent Formation. '56 to 50 million years old. 56 to 50. That's not the age of accretion. That's the age of the rock. 56 to 50. The accretion of Silesia, the last accreted terrain, happened 50 million years ago. Silesia is 50 million years ago. So, put this together, we've got lava rock that ranges in age from 56 to 50 million years, and it all smashes onto the continent 50 million years ago. Okay, this is sounding interesting. So that's Silesia. That's our final accreted terrain. It's our final exotic terrain of the Pacific Northwest. We're closing in. Hey guys, we are closing in. So let's tell the story of Silesia. Let's tell the story of the Olympic Peninsula. And let's tell the story of, oh, can't do it yet. Oh, I started drawing that map too big. Sorry, stand by. All right. One last crappy map for old time's sake, right? Here we go. Washington, Oregon, Cali, Nevada, you know it. 60 million years ago. Let's go 60 million years ago. Off southern Oregon and California, off the coast, was a basalt mountain, a basalt volcano, a very large one. It's called Silesia. And it's riding on the Farallon Plate. It's very big. It has approximately 14 times the amount of basalt lava rock as the Columbia River basalts. This is 14 Columbia River basalts that are 3 miles thick at Tri-Cities, right? 14 of those piled up in a mountain. What mountain can you think of that we've talked about in this class that's a giant pile of basalt lava rock sticking up out of the ocean? Kilauea, Hawaii. But this is bigger than the big island of Hawaii. This is a big, big island. It is a big pile of basalt lava rock. I could give you one more pile of basalt lava rock sticking up out of the ocean. How about Iceland? Cool. So here comes Silesia riding eastward on the Farallon Plate. Northeastward, in fact. North America, traveling southwest. We know that. And when this big basalt mountain, this big basalt island, comes in contact with us, comes in contact with North America, it blobs on to the edge, Washington and Oregon. Okay? All right. 6 million years worth of lava blobbing on to the edge of Washington and Oregon. What's that mean about this map? It means that Seattle and Portland, they're right there. They're on the coast, right? We're building the Olympic Peninsula now. We take Silesia, we smash it onto the edge. Smash it onto the edge. And this is not a trivial amount of basalt. This is all of the bedrock basically between the Cascade Mountains and the Pacific Ocean. All of the bedrock is crescent formation. All of the bedrock is Silesia. It's all basalt. There's other stuff on top of it. What about Mount Olympus, right? Scraped off all of that mud and stuff. We got the faults, we got the folds, we got shale up on top of we got shale up on top of Mount Olympus. All that's sitting on top of, it's sitting on top of the crescent formation. It's sitting on top of this Silesia basalt. If we looked at it in cross-section, here's our Olympic Peninsula in cross-section. Right, west, east, Cascades, Seattle, here's our Space Needle. Seattle. Crescent formation looks like that. And then all of this stuff here this is all our folded shales and other random shit that scraped up off the ocean floor. We're getting close. We're getting real close, guys. To make the picture more complicated, it's generally considered that Silesia was actually sitting, straddling, if you will, a spreading center, a divergent plate boundary. And that spreading center, we're actively The North American continent is actively overriding this divergent plate boundary, this spreading center, and there's all kinds of strange lava rock from here to frickin' South Dakota that backs this story up. It's all 60 to 40 million years old. Devil's Tower in South Dakota, and there's strange lavas, there's strange magmas in Idaho and in Montana, all over the place, that are all thought to be related to this divergent plate boundary that we got going here. The plate, long gone, called the Kula plate, not worth talking about for this story. It's also connected to that Baja BC idea, but we're just gonna leave it for right now. We're just gonna leave it for right now. Got one more map to draw for you. I've got one more picture to show you that I think is going to put all kinds of pieces together. I'm going to do this with a little bit more detail and a little bit more care. This is it. This is it for us this year. Maybe I screwed this up a little bit, but hey, you know what? It's okay. It's good enough for us. North America. Maybe you're a step ahead of me on this. Maybe you are. What is it? What sort of geologic situation creates a big old mountain of basalt lava out in the middle of the ocean? We're putting together all kinds of lectures here, all kinds of pieces. We're plucking them out of different lectures. What's driving Hawaii? What's building Hawaii? Is a hot spot, mantle hot spot, right? Source of heat, erupting hot spot, sitting on top of oceanic crust, melting oceanic crust, erupting basaltic lava, right? Right. What was Silesia? It was a giant mountain of basalt lava out in the middle of the ocean. $60 million years ago, Silesia was a hot spot off the west coast of North America. Where's the nearest hot spot to us right now that you can think of? Hasn't erupted for 640,000 years. Yellowstone hotspot. Right there, right? Montana, Wyoming, Idaho. Yellowstone hotspot. What was our evidence that North America is moving to the southwest? You remember that trail of old calderas from the Yellowstone hotspot, marching to the southwest, across Idaho. When did that trail of calderas stop? 17 million years ago. $17 million years ago to today, we've seen the exact footprint of where that hot spot has been, or rather where our continent has been over the top of that hot spot. 17 years ago it stops, right? It just stops. What started 17 million years ago? Columbia River basalt. We talked about that whole thing too. Where did they start? Right there. And they worked their way up into Washington. Those cracks, those fissures. So we got about 40 million years to account for. Well, here you go. It is generally accepted among geologists that this hotspot, the Silesia hotspot, and the Yellowstone hotspot are the same hotspot. It's the same vent out of the mantle, and it hasn't moved anywhere since at least 60 million years. So we're headed southwest. We've got this nice trail. I'm going to change colors here because that trail that we did in red there, we know where those are. We can see where those are. And the calderas stop. But do they? Because there's calderas in Oregon too. Did them in yellow. Probably barely make them out. There's calderas in Oregon, but they're going the wrong direction. What's that all about? What about ages? Do we know about ages? Yeah, we do. We know that those calderas in Oregon have changed to orange. The yellow is not dark enough. Those calderas in Oregon are between 20 and 40 million years old. It's consistent with our story, isn't it? Today, 17 million years, getting older and older and older to 40 out here, 60, 50 million years. We've chunked this thing onto the edge of North America. So what is our hotspot zigzagging all over the place? Or is there another thing at play? Is there another part of the story? There is another part of the story. I lost my blue Sharpie down here. And I want to use my blue Sharpie. I got my blue Sharpie back. Are we feeling comfortable with this? This is some advanced stuff. It's the big grand finale. Let's talk about the evidence one more time. We've got a blob of basalt off the coast of North America, which ends up stuck to Washington and Oregon. Do it with a dotted line. That's our crescent formation, right? Silesia sticks on 50 million years ago, our last accreted terrain. There it is off the coast, blobs on to Washington and Oregon. We've got modern day Yellowstone. We know exactly where that hot spot is. There's calderas. There's a line of calderas across southern Idaho, getting older and older and older until it stops 17 million years ago. And we've got some random calderas going northwest through Oregon, starting about 20 million years, getting older to about 40 million years. I'm telling you that this hotspot hasn't moved. And North America has been traveling southwest the whole time. North America has been traveling southwest. So what's up with the change in direction of our calderas through Oregon? Time to put together some more stuff from some different lectures. What color haven't I used yet? I haven't used green. Here's the San Andreas Fault. You remember Pacific Plate dragging northward? Do you remember clockwise rotation of the Pacific Northwest? I'm here to tell you that this line of calderas continues in a more or less straight line all the way back, except that those calderas have been dragged northwards because of the clockwise rotation of the Pacific Northwest. That clockwise rotation, what's that responsible for? It's responsible for all of those faults that we talked about. It's responsible for the Saddle Mountains. It's Washington getting smashed up against Canada. That same clockwise rotation drug all of these calderas and all of that land, it rotated it northward. And if we can roll back time, we're stretching Washington back out and we're straightening out this line of calderas until eventually there's a continuous, more or less straight line from the Yellowstone hotspot where it is today to the spot off the coast of southern Oregon and northern California where Silesia once sat. How about that for a cool combination? How about that for dragging together little bits and pieces of evidence from different fields of study, different types of geology, and using it to tell one big ass cool story. Guys, I'm checking my notes that I made for this lecture, and I'm sad to say that I've gotten to the end of them. This is it. We're done. If you're still watching, you're still with me, thank you. I'm proud of you. I'm proud of you guys for sticking through this. Distance learning has been hard. It's been effed up. And you guys have been total, pardon the pun, rock stars. I couldn't be more proud of you. It's been a real pleasure teaching you guys this material. It's what I live for. So thanks for going on this journey with me. We got practice test coming out. We'll have another little Zoom meeting about it. And then we got the final. And then that's it. We're done. So, for the last time, so long from Ellensburg. Goodbye. I love you. Stay safe, stay healthy. Hope to see you in school next year. Hope we get to go back to school next year. Take it easy, guys.